Okie dokie, folks. We are going to go through this quiz and help you to understand the answers here. So starting with the first question, when you saw the BR2 here, you probably are asking yourself, this is either going to be halogenation or free radical substitution. The UV light should be a clue that it's free radical substitution, but there's another clue here that shows you that it is not halogenation of an alkene. And that is the way halogenation of an alkene works is through an addition reaction. What that means is that the bromine, the Br2 molecule, comes up underneath the double bond, and you get these bonds that sort of shift around that common diagram that we've seen. And the net result is that the bromines end up on different carbons. And you'll notice that here the bromines are on the same carbon. So this did not happen by halogenation. In other words, it didn't happen by addition. It happened via substitution. And a free radical substitution substitutes a halogen for a hydrogen. That's what this substitution means. You take out one thing and put something else in its place. So I've started with something, and I've ended up with two bromines on this what looks like an ethane molecule, basically a dihalogenolalkane. Well, free radical substitution only adds one bromine or one halogen at a time. So if you can sort of imagine, all you're really doing is because we're going in reverse here, we're just going to subtract a bromine and add in a hydrogen. We're going to unsubstitute. So this is going to be CH2Br and then CH3. Okay? Because essentially what I've done is I've removed one of these hydrogens and put a bromine in its place. Well, what would that look like? Well, actually, I can show you really quickly the mechanism for that reaction. Here it is really quickly. Step 1 is initiation. UV light is needed to force the bromine to undergo homolytic fission, and I get two bromine radicals. Step 2 is going to be propagation. There is my bromine radical and my other reactant, the CH2BrCH3. And again, I'm going to get this bond here, and one electron from there, one electron from there, and one electron goes over there to make my other radical. In other words, I get HBr and a radical CHBrCH3. Okay? In my next propagation step, this is going to react with a bromine molecule to make my product. So I get, here's my bromine, and then I get my carbon, or my halogenal radical here, CHBr, CH3. Okay, and then again I get a bond that forms here, one electron, one electron, one electron, creating a bromine radical. Okay, and then for my termination steps, I have all the different possible combinations of radicals. In other words, this radical here could join up with a bromine radical, or two bromine radicals, or two of my halogenolalkane alkane radicals. So the one that I care about the most is when these two combine and I get my product again. So that's going to give me Br and then CHBr, CH3, which is essentially just the same as saying CHBr2, the same as this right here, right? Because I have two bromines on that carbon there. Okay, I'm not writing out all the termination steps, but they're there. Okay, that's basically how that one works. Okay, and I purposely put that first question first, and the second question here is an example of an addition reaction, because you'll notice that my product, I have a bromine on two separate carbons. My starting product is an alkene, and I get a dihalogenolalkane, which means I've simply added Br2 to my starting product there. No catalyst or special conditions needed. Okay, number 3 here is an example of a substitution reaction as well. It's a nucleophilic substitution reaction. You should recognize that OH minus is my nucleophile, and I know that the nucleophile is going to attack this carbon. Whether it happens by SN1 or SN2 mechanism, the question's not asking that. It's just saying, what's the product? it's simplifying it for you. And so it is a primary halogenoalkane, so it does undergo SN1, but regardless, the nucleophile attacks the primary carbon at the end. And so essentially, this F just gets replaced or substituted by the OH, producing a primary alcohol. It's exactly the same molecule, just with an OH written instead of where the F was there. No other catalysts or conditions are necessary. This is a fairly spontaneous reaction. Looking at number 4, you should see this and go, okay, dichromate is used in the oxidation of an alcohol to produce something. So this is the oxidation of an alcohol. I don't know if I would require you on this quiz to specify what other things are necessary, but there are some things that are necessary here as well, like for example heat and an acid catalyst, say H2SO4. Okay, that you should know they're necessary. Whether or not you put on the test or not doesn't matter at this point, but you should know that they're there. So the question is, and what did I produce? Well, looking at this molecule here, CH3, CO, CH2, CH3. Okay, so in other words, I've produced a ketone. And it's really important you're able to come up with that structure, because you can see that a ketone is a secondary structure. The carbonyl is in the middle, not a primary structure. So because it's a secondary structure, it was made from a secondary alcohol. So if you can just simply imagine a secondary alcohol where the OH was on the second carbon, that is your starting product. So it's basically going to look almost the same as that, but it's going to be an OH where the carbonyl is. There's the CH3 on the end, and then you can draw it that way, the CHOH. This is essentially the reactant that I'm writing right there. Okay, leaving me with CH2CH3. Okay, and there's your reactant. Okay, moving on to the next one then. Look at what you're starting with here. Okay, CH, that is it's an unsaturated bond, because there's not enough things around the carbon for it to be all single bonds. So there's a double bond there. This is an alkene. Okay, so there's your starting material, and you're ending up with that there on the bottom. In other words, everything's the same except for I've got rid of the double bond, and now I have an HF where there was nothing. In other words, I've just added HF to my molecule. This is an addition reaction, right? It's not a substitution, it's just an addition reaction, and I've added HF. And that's all that's necessary, because addition reactions are spontaneous when you're involving halogens. Number 6 is a little tricky because it looks a little scary because there's a benzene ring there. There is your starting material, okay? And we don't care what this thing is called. It has a benzene ring on it. It's all we need to know. But we have to recognize that there is a double bond there. Count the bonds around these carbons here. This carbon has a bond to one of those carbons, a bond to that hydrogen, and a bond to this other carbon. That's only 3 bonds, so one of them has to be a double bond. This is the way it looks here, the starting product. And then looking at what your end product is, you're starting, yeah, well, you get what I'm saying. Anyways, again, the benzene ring is unchanged, and this has gone from being unsaturated to fully saturated. So basically all I'm doing here is this is becoming a single bond, and then this is now CH2, CH3. And it's all saturated. It's gone from being an alkene to an alkane. So this is just basically hydrogenation. Again, I've just added H2 to my molecule. That's all I'm doing. I'm adding H2, but we know that hydrogenation is not a spontaneous thing. You need to have a catalyst, specifically a nickel catalyst, and you need a little bit of heat. Let's just say 200 degrees Celsius. Okay, and looking at number 7 here, the polymer question. Remember that we write our polymers as H's, which means that, well, we'll get to, actually, I'm getting ahead of myself here. First of all, let's identify the repeating unit. What is it that's being repeated? And you can see fairly easily, I hope, that this is one repeating unit here. Okay? It's just that thing written over and over again, 3 times in fact. Okay? Well, if you look there and remember that we draw our starting materials for these polymers as H's, and the cross beam is always a double bond. Okay? In other words, that would be my starting material. So look at this here. They're going to circle for you your starting material. I'm just going to draw the longest chain of carbons. There they are there. Okay, if I draw it all in a straight line, it's carbon, single bond, carbon, double bond, carbon, single bond, carbon, single bond, carbon. Okay, and then here I have a chlorine, and here I have a chlorine. That's your starting material. Okay, it says to name the starting material. Well, this is an alkene. Okay, it's pent-2-ene. Whoops, pent-2-ene. Right? 1, 2, 3, 4, 5, and this is carbon number, the double bond between carbon 2 and 3. Okay? There are also some chlorines on there, on 2 and 3. This is going to be 2,3-dichloro. Pent-2-ene. There you go there. Okay? And looking at number 8, this is a detailed description of how you convert an alkene to a ketone. Okay, this is where it's really handy to be able to picture that reaction diagram. Okay, remember that alkene is in the middle, okay, and then ketones are down here at the bottom. Sorry, my pen's being all funny. Okay, and I can't go directly there. I have to first of all go here to alcohol. Okay, so I can go from an alkene to an alcohol, and from an alcohol to a ketone. But that only happens if it's a secondary alcohol. Okay, and so I need to make sure I produce a secondary alcohol from my alkene. All right, so there's two different reaction steps there. All we have to do is list the reactants, any conditions needed, and the significant products produced. Okay, so there's hex 3-ene at the bottom, and the first thing is to make it into an alcohol. That's going to be via an addition reaction where my HOH, or water, is going to come from underneath. I can see that the OH is going to attach itself to the third carbon in this chain. In other words, I'm going to produce hexane 3-ol. The question is, what do I need to do that? Well, obviously I need to add water, but in addition to water, I also need something to make this go. And I said that I would use an acid catalyst, H2SO4, and some heat. You can say heat, you can say 200 degrees Celsius, whatever. Heat is fine because if you start saying stuff like 200 degrees Celsius, people might ask, well, isn't that going to boil off the water? It's actually a pretty good question. Logistically, we don't always use 200 degrees Celsius. It's just a way for you to recognize that we have to use some amount of heat. So here we go anyways. That gives me to hexane 3-ol. That's the first step, step number 1. Step number 2 then is to oxidize this alcohol into a ketone. This is a secondary alcohol because this carbon is attached to 2 other carbons, okay? And to oxidize an alcohol, it's always the same reactants. I'm going to react it with dichromate, so Cr2O7 minus 2, or you could say K2Cr2O7, which is just the salt version of it, the ionic version of it. Okay, all I care about, the part that matters, is the dichromate ion. Okay, there are some conditions that I need. Obviously, I need to heat this up, and again, I need a catalyst. And look at that, it's the exact same conditions as the first one. Isn't that nice and easy? And to go from hexane 3-ol to oxidize it, it automatically becomes hexane 3-one. Okay, and that's all you need, just like that. All right, so again, working through that reaction diagram, up to 2 steps you'd be required to do. So have a look at the pink quiz and maybe bring that to school on Thursday complete.